So we've been talking up to this point about Taylor series. So we have a function f of x, and we can build this infinite polynomial f of c plus f prime of c over 1 factorial times x minus c plus f prime prime of c over 2 factorial times x minus c squared. And we keep adding these terms so that we can write it in summation notation as the sum n goes from 0 to infinity of the nth derivative evaluated at c over n factorial times x minus c raised to the nth power. And the whole idea of this was that this was simply a clever way to list the successive Taylor approximations of the function. That is, f of x could be approximated by its tangent line, f of c plus f prime of c times x minus c. But we could get an even better approximation over a slightly longer interval by taking that tangent line and then adding the second order approximation, f prime prime of c over 2 factorial times x minus c squared. Now we saw last time that we could get a hold of this entire Taylor series if we manipulated the Taylor series of known functions using something called the Heredity Principle. The Heredity Principle that we learned last time says the following. Suppose that g of x is obtained from f of x by a sequence of arithmetic, algebraic, or analytic operations. If those same operations are applied to the Taylor series of f of x, and the resulting series can be written in the form c0 plus c1 times x minus c plus c2 times x minus c squared plus c3 times x minus c cubed, then this series must be the Taylor series of the function g, evidently centered at c. Now, we saw last time how we could start off with a known function and then sort of manipulate to get a hold of this Taylor series here. But what I want to do is I want to focus on this piece by itself. Turns out that an expression of this form is called a power series centered at c. Now, a power series is a sort of infinite polynomial that's of the same form of a Taylor series. Like the Taylor series, a power series isn't a single thing so much as it's shorthand for a list of things. There is a linear portion. There is a quadratic portion that includes the x minus c squared terms. There is a cubic portion, which includes all of these guys, plus that extra, that extra c3 times the x minus c cubed portion, and on down the line. Right? A power series, this summation n going from 0 to infinity of these coefficients in front times x minus c raised to powers, is nothing more than a giant list of polynomials. So what is a power series for? Well, intuitively, a power series is a list of approximations whose describing an as-yet unknown function. So the idea is, if you happen to know the name of the function, then you can build its Taylor series, which is a special power series that describes it. The other idea is, if all you know is the Taylor series, you could ask yourself, if all you know is a power series, you could ask yourself, what function is it the Taylor series of? This ends up being one of the most important tools for evaluating what are called infinite series of numbers that we're going to talk about in a couple of sections. But let's see if we can do this by an example or two. So let's see if we can find the function f of x if it's known that the Taylor series of f of x is 1 plus 5x plus 25 over 2x squared plus 125 over 6x cubed plus 625 over 24x to the fourth, and all the way down the line. So how would we go about finding a function like this? Well, pretty much the only tool in our toolkit for manipulating entire Taylor series is the Heredity Principle. So I want to see if I can figure out how to use the Heredity Principle. We saw last time that the biggest trick in the Heredity Principle is simply figuring out who your closest relative is. All I've got now is this. So, who is the closest relative? That's actually a hard question to answer in general, but there is a useful rule of thumb for trying to at least figure out what we're shooting for here, and that's to look for factorials. if you can find factorials in the series, you can figure out the best starting bet. So, are there any factorials in this? Well, let's take a look at what's going on here. I'm going to sort of rewrite the series a little bit. These powers in the numerator are actually just powers of 5, right? It's 5, there's a 5 squared, a 5 cubed, a 5 to the 4th. So those aren't factorials there. But if I look in the denominators here, these numbers 1, 2, 6, and 24, well, 2 is 2 factorial, 6 is 3 factorial, 24 is 4 factorial, and 1 is obviously 1 factorial. So there are, in fact, lots of factorials in here. I've got a 1 factorial, 2 factorial, 3 factorial, and 4 factorial in the denominator. Now, of our 4 basic prototype power series, Taylor series, only one of them has all of the factorials in it, the sequence e to the x. And so that's what I'm going to start off with. Again, this is experience talking to me here. I know that I use the factorials to sort of make an educated guess as to who my nearest relative will be. And then we're going to attempt to do the heredity principle, based off of lots of examples we saw last time. So one of the common things we did is we blanked out the variable, just to sort of get us some wiggle room here. Let's see, what could I possibly do to take this series here and make it look more like this series here? Well, since these 5s are going up by powers, we saw yesterday that that seems to happen quite a bit when you make a replacement. So it would suggest that I could go and put a 5x in each one of these blanked out spots. If I did that, well, let's see, we'd have e to the 5x has the Taylor series 1 plus, this is 5 over 1 factorial x. This would be 5 squared x squared, so 5 squared over 2 factorial x squared. This would be 5 cubed x cubed, so 5 cubed over 3 factorial x cubed. And then 5 to the 4 over 4 factorial x to the 4th. And what do you know? It's a perfect match. And so we've just found out that we're looking at the Taylor series for the function e to the 5x. Now the best way to do this is with practice, so let's just take a look at several more examples. Let's find a function whose Taylor series is given by 1 minus 9 over 2 factorial x minus 2 squared plus 81 over 4 factorial x minus 2 to the 4th minus 729 over 6 factorial x minus 2 to the 6th. So who could this function be? Well, I'm going to use the idea from last time that the first thing I'm going to check is I'm going to check for factorials. In this problem, I see 2 factorial, 4 factorial, 6 factorial. I see the even factorials. And of my 4 prototype functions, there's only one of them that has factorials in it. 1 minus 2 factorial x squared plus 1 over 4 factorial x to the 4th minus 1 over 6 factorial x to the 6th plus 1 over 8 factorial x to the 8th. Do you remember who it is? It's the even trig function cosine of x. So this is going to be where I start my search, with a near relative. Now, doing what I do quite a bit, I'll blank it out first so that I have some wiggle room about what to make substitutions for. Now, what I'd like to do is I would like to get this series to look more like this series. So an obvious candidate would be to replace all of the blanks with an x minus 2. If I do that, I get all of these terms, but I somehow don't get any of these weird numerators here. So I got to figure out what the pattern is in these numerators. Well, actually, it looks like the numerators are going up by 9s. And since these are going up by powers, this happens an awful lot when we make substitutions. So maybe this was the wrong substitution to try. What if instead we took cosine and we replaced it with 9 times x minus 2? That would give me the series 1 minus, sorry, there was a negative, I didn't catch it last time, in 2 different spots. Man, I was terrible at that. 1 minus 1 over 2 factorial blank squared, where the blank is now 9 times x minus 2, plus 1 over 4 factorial times blank to the 4th, where the blank is 9 minus x over 2, minus 1 over 6 factorial times blank to the 6th, where the blank is 9 times x minus 2, And so if I do that, that would be 1 minus, let's see, 9 over 2 factorial. Oh no, it will be 9 squared times x minus 2 squared. And then the next piece would be 9 to the 4th, x to the 4th. Or x to the 2 to the 4th, sorry. And then, let's see, 9 to the 6th, x minus 2 to the 6th. Which is not quite what I want. I wanted this to be a 9, I wanted this to be an 81, I wanted this to be a 729, and we're kind of off by a little bit. Do you see what the fix is? 9 is not the thing we want to replace it with. Whatever we replace it with is going to get squared, so we need to start off with something who's going to square to get me 9. And that would be a 3. So let's try this one last time and see if it works. We've got cosine of blank, who has the Taylor series 1 minus 1 over 2 factorial blank squared, plus 1 over 4 factorial times blank to the 4th, minus 1 over 6 factorial times blank to the 6th. And we're going to try making a replacement with 3x minus 2. So if we do that, well, let's see, we're going to have 1 minus, this will be 3 squared, or 9 over 2 factorial, x minus 2 squared. The 1 over 4 factorial. Here we're going to have 3 to the 4th. That's 3 times 3 times 3 times 3, which is 81, times x minus 2 to the 4th power. And then here we're going to have 3 to the 6th power. That's 9 cubed, and 9 cubed is 729. And so here we actually have it. It turns out that we were looking at the function cosine of 3x minus 6, centered at 2. This example shows that while the basic idea of the heredity principle is pretty easy to apply, working on the series side, you're going to sometimes make false guesses. You're going to sometimes substitute something too early, or maybe substitute the wrong value. So when it comes to doing this kind of problem, which is sometimes called a reverse heredity problem, you're going to have to be willing to make some attempts and fail a couple of times. Find the sum of the power series summation n goes from 4 to infinity x to the n over 2 to the 2n. So the first thing is, what does this actually mean? Find the sum of a power series. Finding the sum of a power series is the same thing as finding the f of x with this as its Taylor series. It's just sort of a shorter way of saying that. So it's just another way of doing the same problem we've done in the previous two examples. So in other words, we're trying to find a function whose Taylor series looks like summation n going from 4 to infinity of x to the n over 2 to the 2 to the n. Now if I write out what those terms are, just so I get an idea of what this series looks like, that's going to be x to the 4 over 2 to the 8 plus x to the 5 over 2 to the 4, 5 times 2 is 10, plus x to the 6 over 2 to the 12, plus x to the 7 over 2 to the 14, and on down the line. So that's the series we want to play around with. So I want to apply the heredity principle. That means I want to start off with a near relative and then, well, see what his descendants look like. What would be the best relative to start off with? Well, let me use that factorial method I was talking about before. In this case, I don't see any factorials in any of the terms. So, is there a function whose Taylor series doesn't have a single factorial in it? Yeah, the geometric series function, 1 over 1 minus x. So that's where I'm going to start off with. The geometric series 1 plus x squared plus x cubed plus x to the 4th. And then see what I can do to manipulate it. So the first thing I'm going to do is blank stuff out, because, well, it seems like that was a fairly common trick last time, was to make replacements. So now what kind of replacement can I make? Well, experimenting around a little bit, I mean, I see that there's powers as x's, so certainly I'm going to have x's running around in here. There's also what appears to be powers of 2 going up in the bottom. So I'm going to try x over 2 as a starting guess. It may not be perfect, but maybe it will get me there a little bit more quickly than, or get me in the ballpark. So when I do that, we're going to have 1 over 1 minus x over 2 has the Taylor series 1, plus x over 2 plus x squared over 2 squared plus x cubed over 2 cubed plus x to the 4 over 2 to the 4. Now, that's not quite what I've got up here on this line above. Remember, this is the series we're trying to build. All of the terms in the series above start off with an x to the 4, and they also start off with a 2 to the 8. Well, maybe I could do that by simply multiplying both sides of this series by x to the 4 over 2 to the 8, and seeing what I get. So if I do that, on the left-hand side I'm going to have x to the 4 over, and distributing through, that's 2 to the 8 minus 2 to the 7x. And then if I distribute through on the right, I'm going to have x to the 4 over 2 to the 8, plus x to the 5 over 2 to the 9, plus x to the 6 over 2 to the 2 squared, 2, 8, 2 to the 10th. And then I'll have 2 to the 7 over 2 to the 11th. And that's the series I get. Does it match? No. I'm not getting the right denominators. The denominators I've got on the bottom started at 2 to the 8th, but they were marching up by, well, a power of 1 each time, whereas in the original series they were marching up by a power of 2. But it seems pretty close. So what can I do? Well, another useful sort of rule is that when you're dealing with powers who are going up, that's usually affected by the substitutions or what you multiply by. Could I change either one of these things? Could I change what I multiply by? Would that have affected anything? Well, not really, because whatever I multiply by, these powers were marching up by 1s each time, and simply multiplication is just going to shift those powers up or down. So I need to change my substitution. If you stare at this long enough, you might catch that the main problem that's happening here is that you've got these powers, and those are the things that you're going to raise whatever's in the parentheses to. And since these powers are only going up by 1, well, then the powers of 2 are going to go up by 1. Is there a way that you could make the powers of 2 go up by 2s? Well, actually you can, and it just makes one slight change in what you're going to substitute in. Instead of substituting in x over 2, let's try substituting in x over 2 squared. So imagine I put a 2 squared in all of these places. So on the left-hand side, we're going to have the function 1 over 1 minus x over 4. And on the right-hand side, we have 1 plus 1 over 2 squared x plus 1 over 2 squared squared, which is 2 to the 4th x squared, plus 1 over 2 squared cubed, that's 2 to the 6th x to the 3. And then we have 2 to the 4, 2 to the 2 to the 4, that would be 1 over 2 to the 8th times x to the 4th. And at least now our powers are jumping up by 2s instead of 1s each time. So we're getting a little bit closer there. Well, let's try the same trick now. Let's see if we can multiply this whole thing through by x over 4, or x to the 4 over 2 to the 8th, to make this first constant match up. So if I distribute through on the left, I'm going to get x to the 4 over, let's see, 2 to the 8th times 1 is 2 to the 8th. 2 to the 8th times 1/4 is 2 to the 6th. And on the right-hand side, we're going to distribute this guy into each one of these pieces. So I distribute these things through, I'm going to get 1 over 2 to the 8 times x to the 4. And then see, 1 over 2 squared times 1 over 2 to the 8 is 1 over 2 to the 10, x to the 5. 1 over 2 to the 4th times 1 over 2 to the 8th is 1 over 2 to the 12th times x to the 6. 1 over 2 to the 6th times 2 to the 8 is 1 over 2 to the 14th times x to the 7. And that's the series we get here. And so, again, we want to compare. Is this the same as the original one? Yeah, with the exception of me putting the x's on top, it's exactly the same power series. And so we've just found out that the sum of this series is x to the 4 over 2 to the 8th minus 2 to the 6x, which I guess we could simplify as x to the 4th, over 256 minus 64x. And so that's its Taylor series, centered at 0. let's sum the power series summation n going from 0 to infinity n times x to the n. In other words, we want to find a function whose Taylor series is summation n going from 0 to infinity n times x to the n, which if we write out is going to be, let's see, n equals 0 gets me a 0. Then I have 1x to the first plus 2x squared plus 3x cubed plus 4x to the fourth, and on down the line. So let's see if we can start off with the heredity principle, find what we think is the nearest neighbor, and then see if we can evolve our way here. Now, taking a look at these guys, once again, I don't see in any of these coefficients factorials. And since I only know one function who doesn't start off with a factorial in its power series expansion, 1 over 1 minus x, let's start there with its Taylor series. 1 plus x squared plus x cubed plus x to the fourth plus x to the fifth. And then I'm going to blank things out just because it gives me the most blank canvas to work with, and then see if we can figure out what we should try to do. Now on this one, the only thing that's going up by powers are the x's. These numbers in front, the 2, the 3, and the 4, they're not going up by powers, right? It's not 2 squared, 2 cubed, 2 to the fourth. And so it wouldn't make any sense to go and try to replace all of these things, say, by 2x, because the minute we replace it by 2x, we're going to have 2 squareds, 2 cubes, and 2 to the fourth. That's not going to be the 3 and the 4 and the 5. In fact, you might be able to convince yourself that nothing you'd stick inside these blanks will get you numbers going up in sequence, because they're always going to be going up by powers. So maybe it's not a substitution. So maybe I need to go back to the original polynomial and try something else. Any ideas on what to do with this power series here? Well, one idea is I'm seeing constants in front, so maybe I could multiply something through. But what would you multiply through? You can't multiply both sides of this by 2, because then I would have a 2 plus a 2x plus a 2x cubed plus a 2x to the 3, and that doesn't match. And I couldn't multiply both sides by a 3, because I'd have the same problem. Instead of it just being a lot of 2's, I'd have a lot of 3's. So I'd be able to get the 3x cubed part to match, but none of the other ones. But what if you tried to take a derivative on both sides? Now on the left-hand side, the derivative of this, well, let's see, we're going to prep it. It's 1 minus x to the minus 1, so the derivative will be negative 1 minus x to the negative 2 times the derivative of the inside, which is positive 1/2. On the right-hand side, if we take the derivative, we're going to have a 0 plus 1 plus 2x plus 3x squared plus 4x cubed plus 5x to the fourth. And actually, that means we've got 1, 2x, 3x squared, 4x to the fourth. We've been able to get a hold of those numbers 2, 3, 4, 5. It's not an algebra trick that gets them, it's a calculus trick that gets them, a derivative. And so now we've got that the Taylor series of 1 minus x to the negative 2 is this power series right here. I've been able to get a hold of the 1, 2, 3, 4, 5's, but it's not quite a match, because I don't have the right powers of x here. The original term started off with an x, and this one was supposed to be an x squared, and this one was supposed to be an x cubed, and this one was supposed to be an x to the fourth. But that should be easy to fix. Let's just multiply both sides of this equation by x. So on the left-hand side, we're going to have x over 1 minus x quantity squared. And on the right-hand side, we're going to have x times 1 plus 2x times, or x times x, plus 3x squared times x, or x cubed, plus 4x cubed times x, or x to the fourth. And there we've got it. The series nx to the n sums to the function x over 1 minus x quantity squared. And so we have an answer. Now, when we've been talking about the Taylor approximations, we've had in the back of our mind something like this. We have a function. If we picked a center, say 0, then the Taylor polynomials construct a sequence of approximations, starting with a tangent line, and then becoming more and more precise an approximation as time goes on. So these are in fact the Taylor polynomials for the sine function. Each frame in this animation represents another term being added in. This is actually a plot of the 29th order Taylor polynomial for sine, and on the interval from -10 to 10, I can't really tell the difference between it and the original function. So again, we go from a straight line approximation, unfolding it back down, to an approximation of the entire function. Every time I add a term, I get a little bit more data. As another example, here's the exponential curve. If we say take the Taylor series centered at 0, then we would have a tangent line, a tangent parabola, and a tangent cubic, and a tangent quartic, and quintic, and so on. Every new term adding a little bit more data and making the approximation push a little bit farther than it was before. And here I am, 16, 17 terms into the Taylor series, and at least on the interval from -5 to 5, I can't see the difference between the polynomial and the exponential. This is what we've been using. This is what I've been selling you on the use of the Taylor polynomials for. Unfortunately, I haven't been completely honest with you. Here's a plot of the function 1 over 1 minus x. You might notice that there's a giant vertical asymptote that's running right through the point x equals 1. But when I'm working with 1 over 1 minus x, I can build the Taylor polynomials, starting with a tangent line, and then at each step of the way, a tangent parabola, a tangent cubic, a tangent quartic. And as I add a new term to the Taylor polynomial each time, it does become a better and better approximation. And that approximation moves forward a little bit more. But unlike the other examples, it doesn't seem like we're getting much farther at all. In fact, 30 terms in, I've got a beautiful approximation of the curve between -1, here's the curve, and +1. But I'm not approximating anything past -1, and anything across here. What's happening? Well, let me try another example to sort of show you what's going on. The square root function. Here's a plot of the square root function. Let's take a look at what happens to Taylor polynomials who were centered at 4. So first we'd have the tangent line at 4, and then we'd have tangent parabolas, tangent cubics. Now as I move forward, each new term makes the approximation extend out a little bit more and become a little bit more accurate. Here we are, 15 terms in. Now, if I were to go farther than 15 terms, watch what happens as I speed it up. Here we are, 30 terms in, and in 30 terms, the function is being extraordinarily well approximated by the curve. But the curve seems to be breaking down right here at about 8 units. Right here's the 50th approximation. Here was the 49th approximation. And if I go back and forth between these two, we can see that it didn't seem as though it was approximating much past 8 at all. Now what's happening? Let me do one last example. Let me see what happens if we set the Taylor series. Same function, but let's build its tangent lines out from 1. Now, just like last time, I will start doing Taylor approximations and seeing what happens. So here I am, 30 polynomials, 40 polynomials, 50 polynomials in, and what I'm seeing is a decent approximation of the curve on a small interval, but it seems to be breaking as we get closer and closer to 2. What's happening here? Imagine that you have some kind of a function, say a function who looks like this, but it has an asymptote, or some kind of singularity. So a singularity might be a discontinuity, it might be an asymptote or a break in the function, it might actually be a place where it's not differentiable, some place where the function or one of its derivatives has gone awry. Now if we start building a Taylor series, say centered right here at C, we've seen how the Taylor series work. Taylor approximations approximate the function over intervals that get a little bit longer and a little bit longer each time. They become better and better approximations. But one of the things you might have caught in our animations is that they're always pretty much a symmetric approximation, that they're pretty much equally good, the same distance from the center on either side. Now the problem is imagine you are this Taylor polynomial and you're doing your best to mimic the function. So you keep trying to mimic more and more and more of this asymptote. Now you're a polynomial, so no matter what, you're always going to veer away from the asymptote sooner or later. So you spend all of your effort trying to approximate this polynomial. This asymptote, sorry. But because that means you're only moving a little bit to the right each time, the left-hand side can only move tiny pieces as well. And so what happens is, visually, you only get a partial approximation. You only end up getting an approximation from the center to the discontinuity, and then an equal distance in the other direction. But the polynomials simply do not propagate their accuracy past here, or they never get their accuracy out here. This is sometimes called a finite radius of convergence. And it represents the main kink in the sort of the armor of the Taylor polynomials, is that they may not be able to approximate the whole function, even if you let them run forever and ever and ever. If it was only a discontinuity that caused problems, then Taylor series would be easy to work with. I say start a series who is centered here. I see that there's a singularity right here. Right, this is a place where f prime of x has gone bad. And so I would say, if I was going to be building with a Taylor polynomial, then I would expect my Taylor polynomials to start building their way outwards. They would be able to build right up to this point, but go no farther. So I would measure that distance, and then I would know that they would go that far to the other side. And it would stop right here. And so my Taylor polynomials would only describe this one tiny portion of the graph. So if you had a completely continuous function, no derivatives, no problems, nothing else, then we would expect that if we centered the Taylor series at any point, that Taylor series would propagate outwards forever and ever and ever on both sides. Right? It's what we've seen with e to the x. It's what we've seen with sine and cosine pictorially. That would be completely obvious. And unfortunately, it's not true. Just consider a story of two bell curves. Here are two classic bell curves that are used in probability and statistics all the time. 1 over 1 plus x squared and 1 over e to the x squared. They have all of the same basic features. They have a high point at 0, 1. They have horizontal asymptotes of 0 as you move out to either side. They've got a pair of inflection points on either side. They are qualitatively, at least, identical curves. However, look at what happens when we look at their two Taylor approximations centered at 0. So here's the function 1 over 1 plus x squared, the first of our two bell curves. If we plot the tangent line at 0, the center, where we're going to get that tangent line, but as we add more terms to get better and better polynomial approximations, we get a little bit more accuracy with each step. But as we're moving on, here we are looking at the 40th and then the 50th Taylor order polynomial. It's becoming clear that the accuracy of these Taylor polynomials is not propagating past plus and minus 1. Even though this function is not discontinuous anywhere, it's a completely ordinary function, just take its derivative. The Taylor polynomials do not seem to be propagating much past 1 in either direction. Now let's compare that with the other bell curve, 1 over e to the x squared. It hugs the axis a little bit faster, but other than that, it's pretty much another bell curve. But if we start plotting Taylor polynomials, just like we did last time, adding a new term of data at each point along the way, then we notice that we've already burst past that plus and minus 1 root. And as I keep moving farther and farther and farther to the right, I see accuracy propagating farther and farther and farther out. 60 terms, 70 terms, 80 terms, 90 terms, and after 100 terms, I seem to have the entire function, at least on the interval that I've plotted it. So once again, here is a function, a bell curve, that Taylor polynomials approximate completely. But here is a bell curve they do not. What's the difference between these two bell curves? What could make one have Taylor series who break down and the other not? Well, I'll answer that question in just a second, but you should be thinking in the back of your mind the genetic metaphor. In the first example, the Taylor polynomials only propagated about 1 unit away and then stopped propagating. In other words, we could say that the Maclaurin series here had a radius of convergence that was equal to 1. A finite radius of convergence, 1 unit on either side. However, when we looked at the second one, it appeared as though its Taylor polynomials propagated all the way down on either side. And that's actually true. This guy has no finite radius of convergence, or, because we like to be able to use this phrase, we're going to say that it has a radius of convergence that was infinite. It just goes and goes and goes. It never comes to a stopping point. Now the graphs are almost identical. There's no visual way to kind of distinguish between the two of them, but one of them has a radius of convergence and the other one doesn't. And the secret is not in the functions, but in their ancestry. If we start with 1 over 1 minus x, then we can get to 1 over 1 plus x squared by a single substitution. We replace x with negative x squared. On the other hand, if we started off with e to the x and made the exact same replacement, then we would end up with e to the negative x squared, which is 1 over e to the x squared. In other words, this function here is a descendant of a discontinuous function. He doesn't have a discontinuity, but somehow his Taylor series has encoded it. On the other hand, this polynomial, or this function here, is a descendant of e to the x, who has a Taylor series that goes forever and ever and ever. And he has inherited this trait. So this idea of the radius of convergence is something that's hidden in the Taylor series itself, not the graph, not the formula, but the Taylor series. So let's summarize what we've just seen. For any function f of x, and any choice of center c, there exists a number r which is greater than or equal to 0 and less than or equal to infinity. And it has the property that the Taylor series of f centered at c only approximates the function on the interval from c minus r to c plus r. That is, it only approximates the function inside the radius of convergence, starting from the center and propagating outwards. Moreover, the Taylor polynomials completely fail to make any kind of approximation of the function outside this interval. Individual polynomials get worse and worse approximations, actually. This value r is called the radius of convergence. Now there's a couple of things worth noting about the radius of convergence. Fact number 1. The accuracy of the Taylor series may or may not propagate to the endpoints. So, for example, you might have the Taylor polynomials accurately propagate what happens at the left endpoint c minus r, but it might fail to get a decent approximation at what happens at the right endpoint, c plus r. That's a possibility. Second, the radius of convergence can be infinite. It could have accuracy who propagates over the entire real line. Of our 3 prototype functions, this is true of the function e to the x, sine of x, and cosine of x. This can be checked using, for example, Taylor's estimate. If the function has a discontinuity at some point d, then the radius of convergence can be, at most, the distance between c and d. Doesn't necessarily have to go exactly that far, but you'll never get accuracy to propagate any farther than that distance. So discontinuous functions always have a finite radius of convergence. Only a continuous function can have an infinite radius of convergence, but as we've seen in the bell curve example, not everyone does. That brings us to the fourth bullet. The finiteness of the radius of convergence is an inherited trait. If a function has a Taylor series with a finite radius of convergence, then the Taylor series of any of one of its descendants, any function we get by starting with that Taylor series, will also have a finite radius of convergence. It's worth pointing out that it's only the finiteness that is an inherited trait. The actual physical radius of convergence isn't fixed in all of its descendants. But if you happen to know a function who has a radius of convergence of 1, then you can be guaranteed that all of his descendants will have a finite radius of convergence ever after. And so that's going to bring us to our final question. Suppose you have a function, this function right here. You're going to build a Taylor series centered at the point C, and you would like the Taylor series to have accuracy who propagates out to this point A. Then how do we know if the Taylor series who starts here and starts building the function outwards in small pieces will eventually approximate out to A? Will it eventually get that far? In which case we can numerically approximate A with polynomials, or will the accuracy stop at a finite radius of convergence away from C, just out of the reach of A? Our goal in the next several sections will be to answer this question. Given a point A, will the Taylor series eventually approximate it? And given any power series at all, can we figure out the radius of convergence?